Welcome guys to today's class. In today's video, we want to see another aspect of simple pendulum experiment. Before now on our channel, both in Chidon's Daniel YouTube channel and the Chidon's Academy Practicals Physics channel, we've discussed the first aspect of it, which involves how to get the readings, so to speak, without touching apparatus. We saw how to manipulate your readings, how to get your reading if you don't want to touch the apparatus. That is one. We also look into how to perform experiment on simple pendulum using principle of cantilever. Principle of cantilever. That means ruler clamp on a desk and you now what displace it small, it will be what rotating up down. You'll be doing your counting. Just rotate it at a small angle, it will be moving up. That is principle of cantilever. Then we want to now look into principle of spring, spiral spring. Yes, we can perform simple pendulum experiment using spiral spring. When you have a spiral spring and you fix a mass on it, the mass, when you stretch it small, it will be moving up, down, up, down, up, down. So when you fix the mass, you will get extension. And from there, if you displace it to undergo oscillation, it start moving up, down, up, down. And so this experiment has been performed in the laboratory. We have performed it and we got this table of values. And the question is, we should do justice to it, plot your graph, answer all these questions that follows through. Okay, this is experiment extension. Now please permit me to convert this extension to meter. This extension is in centimeter. So to convert it to meter, I will divide everything here with or by 100, so to speak. I'll divide everything here by 100. That means I will change this to be a meter. Please, here must be a meter. So if we are dividing this by 100, you will be having 4.1 divided by 100, 0.04. 4.1 divided by 100 is equal to 0.04. 8.1 divided by 100, you have it to be 0.08. We are changing it to meter so that everything will be in SI units. Then this one divided by 100, 12 divided by 100, 0.12. Then this one 0.16, this one 0.2, and this one 0.24. So I've put everything to be in SI units, okay? So that means what I wrote here before is not in meter, it was in centimeter. It was oversight, okay? No one is perfect. So it's in meter. So I put it to be in meter now. Now to get your T. Before now, we have this mentality that to get your T, you say that T is equal to T over what? N, small t over N. And we say that N is 20 oscillation. Mind you, it's not a more that the N will be 20. In this experiment, it was at 30 oscillation. In some other experiment, it is in 10 oscillation. It depends on the instruction given to you. And so, what you have to do is that you have to be dividing everything here by 30, one after the other. 13.4 divided by 30, 0.446. So approximate it to be 0.45. We carry it as it is in the calculator and square it. It will be giving us 0.20. You do it again, 18 0.3 divided by 30, you have 0.61. You square it as it is in the calculator, you have 0.37. Then 21.5 divided by 30, that will be giving you 0.72. Okay, square it as it is in the calculator, you will be having it 0.51. 25 divided by 30, we'll be having it to be 0.83. Square it as it is in the calculator, we'll be having it to be 0.69. 27.5 divided by 30, we'll be having it to be 0.92. Square it in calculator direct, you have it to be 0.84. 30 divided by 30, we'll be having it to be 1.00. Square it, 1.00. And this becomes your table of value for your graph plotting. Now they say using two separate graph sheets, plot graphs of m against extension e and m against t square. Determine the slopes of the two graphs and their standard errors. Given that m equal to ke and t equal to 2 pi square root of m plus mo all over kg, where k is the spring's force constant and mo is a constant, deduce the values of g and k from the graph and indicate its SI unit. This is just instruction. Now we'll be taking the first one, which they said m is equals to ke. You compare it to y equals to mx plus c. That means if you plot the graph of y against x, m becomes your slope. So c become the intercept. Here there is no intercept. So you now say m equal to ke, therefore k becomes the slope you will get in that experiment. So when you plot the graph of m against ke, what becomes your slope is what you call your spring constant, the spring force constant k. Okay, so first thing you do is that you note your title, a graph of what? Mass in kg against what? Against E in meter. Then you write your date. Whether you are instructed to put everything in SI unit or not, if it's very possible for you, make sure everything is SI unit. You will get higher mark when everything is in SI unit. Okay, so I can come up here and put my mass in kg, and come here, put my E in meter. That is labeling your Cartesian axis. We have your E to go this way and we have your M to go this way. Now it's left for us to choose our scale now. If I start 0,0, here will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So it can go like that. 0.10, 0.20, 0.30, 0.40, 0.50, 0.60. That is about this. If you want to know how to get appropriate scales, are you getting? Appropriate scale simply means a scale that will be suitable for that graph, so that it will cover at least 2/3 of the graph. It's not a scale that you will use and some part of your graph will be very vacant, empty space. No, we don't do that. So if you want to get more information on how to choose appropriate scale, just type Chidon's Daniel like this, Chydonnl. Chidon's Daniel, how to choose appropriate scale in graph plotting. Daniel how to choose appropriate scale in graph plotting. You will be able to see the video and many other videos posted on that channel, and you watch and learn. That is by the way. And so we have gotten this. We are now experts in choosing a scale. So we wasting our time choosing the scale. We don't have it. Then for your t square, for your e, the highest is 0.04 and the highest is 0.24 and lower is 0.04. 1, 2, 3, 4, 5. I can say here 0.04, 0.08, 0.12, 0.16, 0.20, 0.24, 0.28. Yes. Now I will locate the points. 0.1 against 0.04, 0.2 against 0.08, 0.3 against, wow, this type of graph plotting is sweet. Wow, no stress. 0.16 against 0.5 against and 0.6 against. Wow, that is sweet. That is sweet. And so we will locate our line of best fit. We will locate. As you can see, we have gotten our line of best fit. Okay, let's get the slope of it. Okay, change in m is equals to 0.6 minus 0.10. Change in e is equals to 0.24 minus 0.04. And so we will say that our slope, which we say it is our k, is equal to change in m over change in e, and is equal to 0.6 minus 0.1 all over 0.24 minus 0.04. And so we put it this way: 0.6 minus 0.1 divided by bracket 0.24 minus 0.04. So we'll be getting it to be 2.5. Our K, the spring force constant, is 2.5. What is the unit of Y? Kilogram. What is the unit of X? Meter. So that is the unit in SI units. Okay? Now let's see how to plot the second graph. We have gotten our K. That means the essence of the first graph is for us to get our what? K. Now, what is the error in this K? Since everything enters this line of best fit, that means error in K will be equal to 0. Error in the slope K is equal to 0 because everything enter perfectly in the line of best fit. And that is how we take this. We have to plot the second graph because we have succeeded to get the spring constant K, and we are asked to get also our G. We have to get G. We are also to get our MO from the second graph. Let's see how to do it. Okay, let's see how to plot the second graph sheet. So they ask us to plot the graph of M against T square. We'll write the title first. A graph of what? M in kg against T square in seconds squared. Once you write the title, write the date on that graph sheet. Then I want to emphasize on this point: whatever graph you plot, the title, the date, the scale, because this first one I plotted, I didn't indicate the scale, but please indicate the scale. Indicate the scale on that graph. the scale you choose. The y-axis was 2 cm represents 0.1 kg. That is the first one we plotted. And the horizontal axis was 2 cm represents 0.04 meter. And so please indicate the what, the scale you use. Okay, yes, very important. So we have fixed our title and our date. Oh yeah, now go to the equation. We are plotting graph of m against c square. Go to this equation, transform it to linear equation. You have t equals to, carry 2 pi, bring it inside, it becomes square root of 4 pi square. When you are carrying 2 pi inside, 2 times 2, 4, pi times pi, pi square, bracket m plus m0 all over kg. Okay, now carry this square root, remove it by squaring the other side. You have that t square is equals to 4 pi square over kg, bracket m plus m naught. Now see what you have to do. We want to make m subject of formula. That is the essence of this thing I am doing now. To make it subject of formula, carry this, multiply this. We have t square kg is equals to 4 pi 4 pi squared m plus 4 pi squared mo. Then I will carry this to the other side. Therefore, 4 pi squared m is equals to t squared times kg minus 4 pi squared mo. Then divide everything by what? 4 pi squared. 4 pi squared. 4 pi squared. You will be having that m is equals to t squared kg all over 4 pi squared minus mo. That means when you plot the graph of m against t squared, y equals to ms plus c. When you plot the graph of m against t squared, this kg over 4 pi squared will become the slope, and the intercept will be minus mo. That means it will have a negative intercept. Okay, okay. Now we will have this in our mind as we do the plot, because it is from this slope we will get here that we can deduce what our g is and what our mo is. Okay, I can say, plotting the graph of m against t squared, let me come here and what, choose, let's say 0 0.01, 0 0.02, 3, 4, 5, 6. Okay, okay. T squared, I'm checking t squared, the lowest is 0.2, highest is 1. Okay, I can come here and say 0, 0. Yes, so that we can get the negative part of the graph, because intercept is negative. That is why I am giving some space. Then I will now say 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.1, 0.2, 0.3, 0.4, 0.5, 0.60. I've told you guys, if you want to know how to get appropriate scale, watch our video on Chidon's Daniel ways of getting appropriate scale, or how to get appropriate scale. Then come to this side. Here I will be using 0.2, 0.4, 0.6, 0.8, 1.0. Wow, can it go? Can it go by that? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. It can't go by 0.1. Are you getting it? And so we will say, let us use 0.20, 0.30, 0.40, 0.20, please. It's by 2. 0.4, 0.20, 0 point. Okay, I think this one will not go well. Let's check another appropriate scale. Now, for this horizontal, I will decide to start it with 0.1. Because when I say 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.9, 0.1.0, that means it's not a must that you will say 0, that is starting from origin. It's not a must unless it is instructed starting both axes from the origin, then it is a must. But here they did not instruct it. Are you getting it? And so we started the y-axis from the origin, but the x-axis, this is the first and this is the second. The first is x, the second is y. So we say let the first, which is the x-axis, be 0.1 and let the y be 0. Are you getting it? And so this will become 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0. Remember, this is just a sketch of the graph, so it's not a must that your own will go like this, depending on the standard graph you are using. And so be able to check it well, choose appropriate scale using information I delivered in that video and get it well. Okay, 0.1 and 0.2, 0.1 and 0.2, 0.2 and 0.3, 0.2 and 0.37. 37 should be somewhere here. Then 0.3 and 0.51, 0.4 and 0.69, 0.5 and 0.84, and 0.6 and 1. Are you getting it? Once you are done with this, indicate the scale. Please do the same in the one we did before now. 2 cm on the, here is m kilogram, and here is t square in second square. So label your Cartesian axis. Wow, we said we are not starting from here, so look at where your horizontal Cartesian axis is. Okay, we are not starting from the down. Okay, scale on m axis, we said 2 cm represent 0.1 kg, whereas on t square axis 2 cm represents 0.1 second squared. So you have it in your mind, okay? Yes. So we have written our scale use. Now, next thing is for us to what? Locate our line of best fit. So we use our ruler. Okay, you can see the line of best fit already traced. In this line of best fit, you notice that one fall on this side, one fall on the other side. This one remains small to enter the line, this one remains small to enter the line. Now, you notice there is a point I circled, we call it the centroid. Centroid means add up all the values, divide it by what? How many they are? They are 6. You have 0.6. Then add up all these values, divided by how many they are? 6. You have 0.35. Then locate 0.35 against 0.6. You see where? That means every line of best fit must pass through the what? Centroid. Every line of best fit must pass through the centroid. You can also notice that it passes through the what? 0, origin. Origin for y-axis is meeting the y-axis at 0. That means you have to tell them that your MO is 0. MO equals to 0 kg. Okay? Then to get the slope of this graph, let's get it. Let's get the slope. You can trace it like this. To this point, then trace it to this point. So what you now do is you now say change in m equals to, this is what, 0.5 minus 0.10. Okay, then change in t square is equals to 0.8 minus, here is 0.2 and here is 0.3. Let's say 0.23. 0.23. Yes, to get this actual value of this point, say this minus it will give you 0.1 divided by 10. It will now be giving you 0.01. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0.03, 0.01, 0.02, 0.03 plus 0.2, you'll be having 0.23. So this minus this gives you the value for each small bus. Then you now say 0.2 plus 0.01, 0.21 plus 0.01, 0.22 plus 0.01, 0.23, like that till you get to what? 0.29 and 0.30. Okay, now we get our slope. We say our slope is equal to change in m over change in t. 0.5 minus 0.1, 0.4, all over 0.8 minus 0.23 equals to 0.57. What will it be giving you? 0.4 divided by 0.57. You will be having 0.702. 0.702. The unit will be, what is the unit of y as is kilogram, all over what is the unit of s as is second square. So we have located it. Then we have gotten our what? Slope of this. But we said the slope comparing this against t square, plot of graph of m against t square, this become the slope. And in the first graph we plotted, we said that k is equal to 2.5 kilogram per watt meter, whereas the error is 0 kilogram per meter. Please note it. You know, I didn't talk about that unit of the error of that scale. Error of it is 0 kilogram per meter. Please note it. Error equals to 0 kilogram per meter. Please note it. Then for this one, we noted that the slope is what? Slope is equal to 0.702 kilogram per watt meter squared. Right? Yes. Then we want to get the error in that slope. Let's get the error in that slope. But remember, don't forget that this slope is equivalent to, since m is equal to kg over 4 pi squared, is equivalent to kg over 4 pi squared. 0.702 is equal to kg over 4 pi squared. That is the point we need to note. Our MO is what? Our MO is 0 kg, because where it means the y-axis is at the what? At the 0 kg. So if you plot your own and you are getting a negative, you also indicate it. You know, the answer depends on how accurate the result of your experiment is. That will determine the degree of error you will encounter and how your answer will go. Okay, having gotten this, let's get the error. Using the principle of worst fit and what? Line of worst fit and what? Best fit. Since this one is a centroid, are you getting it? And this one didn't work. Okay, this one didn't enter, this one didn't enter. Okay, let's check how we will what? Put it. Okay. So coincidentally, this one is trying to enter. It's trying to enter. So we now say, we put it like this. Okay. This is L2, this is L1. So we have to get the slope of the L2. The slope of L2. Okay. Taking our what? From here to here. And so here. Taking it this way. We said that change in M for L2 is, here is 0.448. That is close to 5. 0.4, okay, let's say 0.47, because it's close to 5. It's close to 0.5. Then minus this one is what? 0.10. Then here for this one, for change in t square. Change in t square of this is what? Change in t square of this is what? 0.8 minus, okay, change in t for this one is what? 0.2. Look at the line. This line. We will note this. We note this. Then we note this. Then we note this. 0.20. Okay? Now, the slope of this one will be slope, the worst slope will be equal to 0.47 minus 0.1. 0.47 minus 0.1 all over 0.8 minus 0.2. Okay? We use our calculator to check it out. 0.47 minus 0.1 divided by bracket 0.8 minus 0.2. So we'll be having 0.62. 0.617. The unit is kilogram per what? Second squared. Kilogram per second square, please, not meter square. Okay, now the error will be difference, modulus of the difference. We just say 0. Anyone can come first, but whatever you get, it must be positive. Minus 0.617. What will it be giving us? 0.702 minus 0.617 equals 0.085 kilogram per second square. So that is the error we will get in the second graph. But we note that our first graph have this slope, and that is for the one of best fit. Okay, let's deduce our G. Knowing that 0.702 is equal to kg all over 4 pi squared, and that k is equal to 2.5. That means cross multiply 0.702 times 4 pi squared all over 2.5. That will be equal to our G. And the unit of G will be meter per second squared. Okay, let's check. 0.702 times 4 pi squared divided by 2.5. You will be having, therefore G is equals to 11.1 meter per second squared. G is equals to 11.1 meter per second squared. Okay, so if you use this worst fit to do it, you will even get its own as 0.617 times 4 shift pi squared divided by 2.5. You'll be getting 9.7. The one of worst fit will be giving you that G. If you are using slope of one of worst fit, you'll be getting your G to be what? You'll be getting it to be 0.617 times 4 pi square all over 2.5. You'll be getting it to be 9.74 meter per second square. And so everything depends on the line of best fit, the way you took your line of best fit. Remember that we are using sketch to do this. Are you getting it? Everything depends on how you choose your line of work. But look at this one now. For the second distance, here entered, here only this one fall out, this one entered, and this one entered. So how many fall out? One and what? Two. Are you getting it? So even the second line of best fit obey the rule that 1, 2, the centroid, then 3, 4. Only this one fall out and only this one fall out on opposite side is equally going well with the line of best fit. So line of best fit for L2 obey the rule of line of best fit, that it will pass through the centroid and the one that fall out will be equal. So if you get this to be what? This, you also get the one of if you get from the one you call line of best fit, you have this, get the one of you have this. That means both of them are line of best fit, but you have to take one as line of best fit and take the other one as line of worst fit. So as this gives you 9.74, it means you can take this to be your line of what? Best fit. Take this one to be the line of worst fit, because it's giving you far from what? Acceleration due to gravity, you know, that is around 9 points. Are you getting it? And so that is about this. Don't forget to please write your precautions. Are you getting it? Write your precautions. Ensure you label your graph very well. Okay, that is about it. See you in the next video on practical. Thanks for watching this video.